Next, this question is interesting. Now I don't need to look at answers yet. Look at the question. Right, look at the question. Just look at the question. I want you to attempt this without looking at the solution. A car of 2.5 meters in length approaches the intersection that's 20 meters wide. Okay, wide being in that direction, not width, but in the direction it's traveling. Right? The car speed is 20 meters per second, and the front of the car is 50 meters from the beginning of the intersection. Right? If the driver steps on the brake now, the car slows at 3.8 meters per second square. If he instead steps on the gas pedal, the car accelerates at 2.3 meters per second square. The light stays yellow for 3 seconds, ignoring the driver's direction time to avoid being in an intersection at the instant the light turns red. Should the driver step on the brake or the gas? Wow, tough question. Well, you have to solve. It's actually tedious more than difficult, but it can be done. All you have to do is use the equation of kinematics, which is s equals to ut plus half at squared. Right? You can decide what's the distance they travel. So, looking at the solution, right? So, what you do in solving a question is to think of the way first, rather than looking at the solution and say, okay, this is what I've done before. You must think of how to solve it, right? So here let's try the both situations, which is to either step on the brake or the gas. Let's try one first. Okay, let's try pressing on the brakes. If he press on the brakes, the distance he has moved will be 20 times 3 seconds plus half at squared. Right. In the time of 3 seconds, he will be outside of the red light. He'll be outside of the intersection. Do you agree? Yes. In the 3 seconds where the light turns red, at the moment the light turns red, he will be outside the intersection. But it's not the end of the story. You must ask whether it's still okay, never mind. Let's answer the question first. If he steps on the accelerator, the car would have moved 70.4 meters, which is not enough for him to clear the intersection because the car is a length. The front of the car would have reached 70.4 meters, which means about 3.1 meters of the car will be still within the intersection. So at this point, right, if you're just answering the question, right, you will say he should step on the gas accelerator. Do you agree? Right, the question asks you, should he step on the brake or the gas? So if you just answer it straight away, right, just answering the question, you should say step on the gas. But if you consider further, sorry, I said it wrongly. He should step on the brakes for him to be not in the intersection, correct? Correct, yeah? But let's explore this question further. If he actually stepped on the brakes, where would he end up when he stops completely? Because in 3 seconds, the velocity is actually still not zero, right? When you take 5.3 seconds to come to a complete stop, and he will end up 50.26 meters. He will be jumping 2.6 meters into the intersection, right? 2.3 seconds after the red light has started. So you know what happens at cross junction, right? When this lane stops, that lane passes, right? So he'll be inside and he has to reverse, right? So actually, it's actually a bad choice. Right? So if I am the driver, right, I should actually press on the gas so that although part of your car is still within the intersection, at the moment it turns red, you still have a short reaction time. When this turns red, that side haven't turned green yet, right? There's a short time before the other side turns green, so he can actually clear the intersection when the other side starts moving. Whereas pressing the brake will actually land him inside the intersection, which is a much trickier situation. Okay? Questions? These are the kinematics parts are actually the simpler ones. They are the ones that you will practice until you are very good with it. So not a big problem to me. Okay. Next, you're on the roof of a physics building 46 meters above the ground. Your physics professor, unfortunately I'm not that tall, is 1.8 meters tall, walking alongside building. No, so you really hate the physics professor, right? Right. So you want to, he's walking at 1.2 meters per second, so that's the usual walking speed, 1.2 meters, leisurely pace. And you want to drop the egg on his head. Where should you drop it? Where do you mark the spot X? Where when he pass by and you drop it. Right, so same thing. We divide out the situation. So how, usually we control in terms of the vertical sense, right? The strategy is to think of it in the vertical sense. How far must the egg drop vertically? 46 minus 1.8. Right, you got 44.2. And you can then calculate the exact timing it needs to hit the head, right? So let's find the vertical direction. This goes to 0 because the velocity, initial vertical velocity is 0 of the egg. Substitute in what you need to do. Right? So just like I said, I take 46 minus 1.8 gives you 44.2. Right? That's essentially just this part. Right? I've just done that in a more intuitive sense. Because half AT square, rearrange, you get t. The time taken for the egg to fall to hit the head should be around 3 seconds. So if it's 3 seconds, and you know that the egg has no horizontal velocity, you will probably just take 3 times 1.2, you should get 3.6 meters away. So you would look down from the building, you will ask a friend to measure 3.6 meters, mark across, the professor marks there and just draw it. Okay. Of course, your professor will have eyes on the top of his head, and you can see it and he will stop, right? Because he's a physics professor. That was a joke, by the way. Thanks. Right, and it's very cold already. All right, we finally finished kinematics, right? The easy ones. We talked about Newton's laws. Now it starts to get a little bit challenging. Right? Now it starts to get challenging. Newton's law comes from Newton's Principia. You can read this, right? But we have simpler versions that we have defined for you in your syllabus. We can use just that, it's the same. Okay? Basically, it means that the object at rest, right, stays in a situation of rest, state of rest, or motion in a straight line, unless there's an external force acting on it. So they use very interesting English that we are not used to. Okay. Law number 2, which is something that you use very often, is that the rate of change of momentum is proportional to the force and in the direction of it. Okay. So law number 2, right? Do know, you don't need to quote, yeah, please don't quote this in your exam paper. The Olympiad teacher will like, what's this? Mark you wrong. Please quote what you have in your definitions for dynamics later on or forces later on, right? So basically the definition will be the rate of change of momentum is proportional to the force and in the direction of the force. There are 2 parts to it. Third one, for every action there's an equal and opposite reaction, or the mutual actions of 2 bodies upon each other are always equal, directed to contrary parts. So the layman or the easier to understand version of in English is when object A exerts a force on object B exerts an equal and opposite force to object A. Right? So I'm translating it to understandable English for you. Simple stuff. Force is a vector, you already know that. Let me not bore you. Sum of forces is just a vector sum of all this. That's why there's all these horizontal arrows on the top of the arrows. So I should do this because your friends at home cannot see me touching the screen. So yeah, look at all these arrows. Yes, it means that they are vectors, and R is the sum of the forces. Textbook notation. Okay, what is this big scary thing? Is a summation sign. You all learn this? All right, cool. You all learned it in secondary school. When did you all learn this? A week ago. Okay. Yep, so this is a summation sign. It means that 1 plus 2, where I is 1. So you start with I being 1, then 2, then 3, then 4, then 2, whichever value that they stay here. Okay? So this is a very usual notation you have to learn. Force is a vector. Let me not kid myself, you already know this to the max. You already know to resolve this. If not, you won't be here. There you go. It goes in all directions, right? Summation of x. So the resultant force in the x direction will be the sum of all the forces in the x direction. The resultant forces in the vertical direction will be the sum of all the resolved vertical forces, so on and so forth. All right, done. This is what I said just now. Body acted on by no net force moves with constant velocity and zero acceleration. This is not very good. You should use the one that we use on Nooks. It's much better. Right? A body stays in a state of rest or motion in a straight line unless acted on by a net force, external net force. Inertia. Right? The tendency of a motion to resist any attempt to change its velocity is called the inertia of an object. A bowling ball is more resistant to changes in velocity than a basketball. We say there is a greater inertia than the basketball. Okay. So inertia is very well demonstrated in this example. We have a train at time 0, not moving, with the girl inside it. So we cut out part of the train, right? The physicists to demonstrate this, they literally cut out part of the train, and then they have the train start moving and accelerating. So when the train starts accelerating, the train starts to have the green arrow, right here, right? To start moving, you see that there's a bigger velocity, but constant acceleration. The girl stays exactly where it is because she's on skates and she has a very good brand of skates where the friction is at perfectly zero. There's no force, no horizontal forces acting on the girl at all. She has to stay where it is with respect to the external observer. Okay, with respect to the external observer, she stays completely at rest. The train moves, she stays there, and in the time 4, she gets a nose ache. Right? Your bloody nose. Other possible situation, right? The train, right, is moving at a certain speed. The girl hit the back of the train already, right? So she okay, and she turned around, and now the train starts to slow, right? So from a fast velocity, the train becomes a slower velocity. The girl having the initial large velocity will continue moving, right? So with no net forces acting on the girl will continue in its original velocity. So she will smack the other side of the train, unfortunately. Right? So you see that her velocity is actually constant over time. Okay. Let's just have some fun. Mass. Mass is the property of the body, independent of the body's surrounding, right? We all know that that's governed by the atoms inside it. Inertial mass, which specifically defines how much inertia an object has. Gravitational mass, determined by measuring the force of an object in a gravitational field. Now the question is this, is the inertia of mass equals to the gravitational mass? Yes, it seems so, right? They actually refer to different things, slightly different in terms of concept, but it happens that they are similar mathematically, right? So we always say that the mass of object is more or less equal to the inertial mass, which is more or less equals to the gravitational mass. However, a common mistake that students make is that they think that mass and weight are the same. It's not true. If I suspend you in space where there's no planets nearby, there's no gravitational field strength, you have no weight. Okay, so mass and weight is not the same thing. Newton's second law, that's what I've said. Moving on. F equals ma. Right? The stronger, the larger the force I act. So what you have here is a dial. Let this be 0, right? This one be 0, and this is 1 unit. So it turns in a circular manner, clockwise manner. So this is 0, this is 1, this is 2, this is 3. So if you pull with a unit force of 1, your acceleration will be 1. You pull with a unit force of 2, a larger force, it will be twice acceleration. You pull with half the force, it will be half the acceleration. Easy peasy. Okay. You pull with the same force for different masses, you have different acceleration. So if you have the same force, twice the mass, you have half the acceleration. Same force, 3 times the mass, you have 1/3 acceleration. Okay? Yeah. I expected. Right. Weight is just application of F equals ma, so F equals mg. In fact, the force we sometimes say W equals mg. Alright, let's try this. Drop a pen and a textbook simultaneously from same height and watch as they fall. How can they have the same acceleration when the rates are so different? Because acceleration is determined by the gravitational field strength. Okay? You feel heavy standing in the lift that accelerates upwards as you move to the higher floor. If you're above room scale, are you heavier? You are not heavier, you just feel a larger force acting on you. So second question, which is more interesting, is that are you actually heavier? You are not. Your weight is a constant because your mass is a constant and the G field on the surface of the Earth is constant unless the Earth gets split to half, which should not happen, hopefully. However, you feel heavier. How many of you actually have experienced this where you actually are in a lift, you feel the lift go up and you feel like you are heavier? Right, good. You're a bit more sensitive, and when the lift actually comes to a stop, you feel actually a little bit lighter. Right? It's the same. When you sit in a car, it goes over a hump, you feel like you're floating up a little bit at that moment of time. You feel like you're a bit lighter, but it's not true. Your weight is the same. The reaction force, which is what you sense, is what that change. Okay? Newton's third law, already mentioned. Moving on. Apple on the table. Drawing free body diagrams that are good is essential in physics, whether you're in the Olympiad or not. So let's look at it. Forces on the apple. Let's use the correct notations that we always say. So F of T on A, so you say call this force Ft subscript. And so F subscript Ta. Right? We usually put the one that we put on as the last alphabet. Alright, so the weight is essentially force of Earth on A, so it's F subscript Ea for the table. So if there is a force of the table on A by Newton's third law, there should be a force of the apple back on the table. Agree? That's right. Okay, so if you have your force of, this one is a little bit more confusing. There is actually a reaction force of your apple on your Earth, right? The Earth is pulling on the apple through weight. There is hence, by Newton's third law, a force of the apple pulling onto Earth. Okay, wrap your mind around that a little bit. Right, so let's see. Acceleration pair, equal forces. So, interesting point of view. I once had a student who understood physics very well and was a little bit funny and ego. So he said, when I move, it's not me moving, but the earth rotating under my feet. Right? It's not technically wrong, right? Because it's about relative position. When I jump, it's not me jumping away from earth, but me pushing the earth away from me. It's technically not wrong, right? Because it's just all about perspective of where your center of obviously the student is a bit more egocentric, right? Right, next, pulling on a rope. Let's look at this. I'm pulling on a rope. These are the forces on the person. So the force of the rope on man pulls this way. The force of the rope on the block pulls this way. A tension force always acts inwards. Right? A tension force always, it can never act sideways. That's one of the misconceptions. And the second one is that the length of the rope is not the strength of the tension. That's the other misconception that I get from time to time, which is horribly wrong. Right? So, however, if you look at the view of the man acting on the rope, however, it pulls on the other direction. Oh? So this is one concept that needs a bit of slowing down. So the man pulls in this direction, the block then feels a force in this direction. This provided that the rope has no mass and the rope does not stretch. Okay. So these are the pair forces. If acceleration equals to 0, m of r is approximately 0. Yep. if the acceleration of the rope is equal to 0, the mass of the rope must be approximately 0. Right? Oh, sorry, if the acceleration of the rope is 0 or the mass of the rope is approximately 0, the force of the man on the rope will be equal to the force of the block on the rope. And these two must be equal. Okay. Right. Ah, good. You all don't have this in your answer to you. Okay, so let's try a bit more interaction. A fly collides with the windscreen of a fast-moving bus, which experiences a greater impact force. The fly, the bus, or both? I give you 30 seconds, think about it, go. All right, your time is up. Who says A? B? C? I say, I'm so happy. You are very good. It's true. They will have the same force. Why? Newton's third law. The force of the truck on the fly is the same as the force of the fly on the truck. Same. Which one experiences a greater acceleration? Who says A? B? C? Is the fly. Alright, it should not be the same because the same force for different masses will have different acceleration. Okay? Which is why if you are driving a lorry, like a cement truck, and you're driving my car, which is a tiny car, because Mr. Ho is not very rich. Not me, let's say somebody is driving a small car and somebody driving a lorry and they collide, right? It's usually the one driving the small car that gets the bigger hit. So you see people who drive motorcycles, right? Who ride motorcycles, it's really very dangerous. Okay? Advice, don't ride a motorcycle. Right? If you're riding a bicycle, please be very, very, very careful. Okay? If you can spare the cash, buy a car. If you really need a vehicle, buy a car for your own safety. Okay? Right, next. Particle will be equilibrium if, just look at this and it's like, okay, to me this is a little boring, but I think I need to go through this for you. If you look at the engine of the car, the upward tension force, the engine is not moving, it's in static equilibrium. The upward force on the engine, which is the tension at rope, must be equal to the weight of the engine. That one is obvious. But you can also consider forces at a point. Right? At this point, the forces at this point, the tension is actually acting downwards due to the rope here. Right? This rope here is having a downward force. This rope here is having a leftward force, and this tension is having an upper right force. Okay, so you actually can draw these forces like this. T3 then can decompose into a vertical component and a horizontal component, and you should have T1 equals to T3 sine 60 and T2 equals to T3 cosine 60. Okay? And which also means that if you know the angle, you can actually calculate the strength of this rope, or rather the tension in this rope. Okay, easy stuff. Which then also allows you to find T2. So this is still quite very basic. Problems? No? Moving on. Tension in elevator. Finally, we have some challenging question, a bit more challenging. The more standard actually. It's not really that challenging, but a bit more interesting. Maybe you have not encountered this before. Elevator and its load have a total mass of 800 kg. The elevator is originally moving downwards at 10 meters per second. It slows to a stop. So it's moving down and it slows to a stop. What's the direction of acceleration? Up. Very good. Okay. And the distance moved is 25 meters. Find the tension in the supporting cable while the elevator is brought to a rest. Right? This is the picture that you have. The acceleration is upwards, right? That's one of the first key thinking points you need to clear. Then applying the equation, which is v squared equals u squared plus 2as, you will learn this very soon. You can substitute in the numbers, and you can find that acceleration is actually 2 meters second square. Knowing the acceleration, you plug in the mass, you can find the net force, right? Remember that the acceleration is due to the net force, right? So if you look at these two forces, T must be larger than weight to have an upward acceleration. Right? So T equals to W plus MA, rearrange, right? Sorry, you have here that the net force is equal to MA, but the net force is just T minus W, okay? Upwards. So T being upwards, acceleration is upwards, take T minus W because W is down. Right? So convention must maintain. Rearrange, you know that the tension is hence MA plus W. Not a big problem, substitute in numbers, you get this value. So when the lift is stationary, the tension in the cable will be less than when the lift is accelerating upwards. Be it coming down and then slowing down, or at a rest and start to move up. Both cases have upward acceleration, right? And in those cases, the tension in the cable system. The opposite is that it's moving up and coming to a rest, the tension will be smaller than its weight. And when it's at the top and starts to accelerate downwards, right, the tension will be less than its weight. Okay? So the most likely situation where it breaks the cable, I hope it doesn't, it's when it's moving up and accelerating up. Right, apparent weight in the elevator, this is the one we talked about. Now if we actually consider a person in the elevator, right, he or she is moving down, but accelerating up. So you do not need to know the direction, you only actually consider direction of acceleration. Considering the forces on the person, N is a force on the person, W is the weight on the person. Right, you can actually do these calculations and find that N, right? Sorry, this should be 490. N is bigger than 490. Acceleration, that is bigger than 0. If N is smaller than 490, sorry, it's an error. Don't think I can change this. That acceleration must be less than 0. Okay. So if you're standing in the elevator, if you want to lose weight, the fastest way is to go in the elevator, stand on the weighing scale, and have it start accelerating downwards. You'll lose a lot of weight. Okay. Well, of course, it's fake, huh? You also know that, right? Oh. Yeah. Yeah, so later on, you will actually learn circular motion. I should be teaching you that soon. And do you know that the Earth is not a complete sphere? You know, right? The radius to the center of Earth is actually slightly larger at the equator, right? You know that, right? Yes, yes. It is. Okay? Take my word for it. I've not seen it myself because I've not walked the whole Earth, but I take what scientists say to be true. So there are two things that are happening. When you are moving in a circular motion, right, there must be some net forces because the velocity is not constant. Right, and because the radius is big, so actually being near the equator is where your weight is the least. Right, so we Asians actually have for the same mass, a smaller weight. All right, next. Any questions until this point? Okay, I should pause the video because if not it gets too big.